I'll start the recording. Yeah, I can see that you're kind of going, yeah, back and forth. So I kind of didn't want to continue while, yeah, I'll continue now. So yeah, so for this part here, I'm talking about the effective nuclear charge again, because in this section here, to answer this question that matters, right? Yeah, sorry about the connection issues. I'm trying to see if I can move to Teams, if that will have a better connection thing. So what I might try next week is I might try to see if we can try the recording on Teams so it doesn't have so many connection issues. I'm just not super familiar with Teams. But even though I'm answering this question right here, what I wanted to do is just kind of practice how to figure out effective nuclear charge over again. So I'm going to do that here. So this recording will have two parts. Yeah, because I was like, what is happening? So if the effective nuclear charge matters and you have to actually figure that out, oh, sorry, right there. Yeah. If the effective nuclear charge matters and you have to actually figure that part out, then it's important for you to see. Can you see it now? Let me make sure it's being shared. Okay, great. Yeah, if the effective nuclear charge matters and they want you to figure that part out, remember the effective nuclear charge is kind of like the resultant nuclear charge. I shouldn't say they never, they mostly ask the effective nuclear charge about the outermost electron. So in this case here, what we will do is the outermost electron, remember, is being blocked or shielded by the innermost electron. So the way they drew this, it almost looks like it's outside the atom. It's not. This is still inside the atom, but you have a nucleus here. So what I was saying is if these inner or core electrons were not there, the valence electron will experience the full +3. But because they're there, they shield the valence electron from getting the full experience, right? So because they are there, they kind of mute or neutralize the nucleus ever so slightly. Each of them neutralizing the nucleus by a charge of -1, -1. So it starts off, if they were not there, with a nuclear charge of +3, but when you add each electron is -1, each electron is -1 and -1. In the end, the outermost electron only feels +1, even though we know the real charge of the nucleus is +3, right? So we need that idea when we're looking at this picture here. Now, the other thing they haven't said here, only the electrons that are in front of the valence electrons can block it. So they can't be on the same energy level, that they can't be in the same row. For me to understand this once again, because when I get into the chemistry details, it was naturally harder for me, the conceptual part, to grasp it because it was all new to me. But if I could make it a way to where it was not new, it was something I experienced, it made more sense. I don't go to a lot of concerts, but I thought about it this way. If you were in a concert, theoretically, the people next to you on either side, if the stage is right in the middle and it's a circular stage, the people on either side of you don't block you. It's the people in front of you that block you from the stage if you have a bad seat, right? So that's kind of what I thought about. I was like, okay, let me think of the electron at a concert, which I would naturally buy cheap seats. The people next to me can't block me because they're not in front of me. It's only the people in front of me that can block me. So think of it this way. The electrons in the lower energy level. Now, this one here will be all the electrons because the electrons are constantly moving around. So even if they appear here now, they will be here the next second. So I should say all the electrons in the lower energy level block the valence electrons. Now, they don't explain all that when you're doing this. So if you don't really get all that, when you get to this question here, you will be like, I don't even know where to begin with this question, right? Not realizing they want you to understand all that before you get to this question. So what I've done here is for magnesium, aluminum, and sulfur, I have drawn some pictures down here of the energy levels we're going to be dealing with, right? So what I did to know I only need 3 energy levels, I looked at where magnesium, aluminum, and sulfur are on the periodic table. So my periodic table is a little back here. And so I know that all their electrons, let me see, oops, erase. All the electrons for these, this is magnesium, right? It's an energy level 3. This is 3. This is aluminum, and this is sulfur. They are all on energy level 3. So all I need is 3 energy levels to be able to fit in all my electrons, right? Because I want to find my blocker electrons. And I mean, you can, I guess you can get it without drawing. I need the tools. I need pictures. I need stories. I need it all. So, because the question says, which atom's valence electrons experience the greatest effective nuclear charge, I prefer to draw it so we can see it. Okay. Magnesium has 12 electrons. Magnesium uses 3 energy levels, right? Energy level 1, energy level 2, energy level 3. That's true of all of these. So I'll go ahead and label energy level 1, energy level 2, energy level 3. Energy level 1, energy level 2, energy level 3. Okay, so I'm going to place the electron. Remember, energy level 1 from the picture only has 2 electrons here and here. So I have 10 more to place. Energy level 2 goes up to 8. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I still only have 2 left over, right? So I'll place this here. Now the way this works in this model, which they're still using biology, this is kind of like the old school one I learned in middle school. They place the electrons separate, right? They don't come together until you're going around the second time. So magnesium has 2 valence electrons. If you've ever had chemistry in middle school, they showed it to you this way. This may be familiar. And in biology too. Let me work on aluminum. Aluminum has 13 electrons, right? Energy level 1 has 2 electrons. Energy level 2 goes up to 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. Energy level 3 also goes up to 8, but I only need space for 3 more, right? Let me check. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've already placed 10. I need room for 3 more. So I'll put 1 up here, 2 down here, and then 3 down here. I'm going to highlight my valence electrons. You can see why aluminum ends up in group 3 because it has 3 valence electrons. Then finally, we have sulfur. Sulfur has 16 electrons. The first 2 go on energy level 1, the next 8 energy level 2. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 2 plus 8, I've placed 10. I have to put 6 more. 1, 2, 3, 4, 5, 6. Okay, now that we are here, oh, all of these are the valence shell for sulfur, which explains why sulfur is in group 6, right? We'll get to this part later on. The valence shell matches the group number. Oh, okay, that's okay. So, where was I now? Now we have to find the last most election. Doesn't really matter here, just pick one. Since I've highlighted the valence shells, I just need to find the last electron. So let me pick one electron to represent the valence shell. Okay, doesn't really matter. Just pick any of them because there's 6 valence electrons here, right? So we're trying to figure out, since all these valence electrons are outer electrons, how many electrons are blocking them? Okay, how many are blocking them? So let's see. We have 2 valence electrons from magnesium, right? How many inner electrons do we have? We just said 10, right? I literally just said 10, right? So 2 out of the 12. So remember, we had 12 total electrons from magnesium, right? 2 of the 10 are valence electrons. So just go with all of them, right? And then 10 are core electrons. 10 are inner electrons. So since the nucleus is plus 10, 12, the valence electrons only experience plus 2. So I'm showing you like this. The nucleus has a charge. The nucleus charge is plus 12. And then when you bring in the core electrons neutralizes plus 12 by bringing in 10 electrons. Therefore, valence electrons experience plus 2, what's the term called? Effective nuclear charge, my bad, plus 2 effective nuclear charge. This is a leftover charge they experience after you bring in the inner electrons, the ones that have quote unquote better seats. So I'll call it here effective nuclear charge. I can't write smaller. Okay. So I'm trying to separate these concepts here, right? This is what happens with magnesium. Now let's look at aluminum. Aluminum started off with 13 electrons, right? 13 total electrons with aluminum. Let's see the breakdown. From the 13 electrons, we said there's 3 valence electrons from aluminum, right? That means the remaining 10 are core electrons. How does this play out with the nucleus charge? The nucleus charge or the nuclear charge, same thing, is what? Plus 13. But remember, only the core electrons can block the outer electrons. How many core electrons do we have? We said right here, we have 10 core electrons. So the 10 core electrons neutralize the nucleus. So we only end up with a plus 3 charge for the outermost electrons. So valence electrons here, valence electrons experience plus 3 effective nuclear charge. Whichever one you pick, they have the same effect, same experience, right? So I didn't even have to pick one in the end. And then finally, we have sulfur. Sulfur has 16 total electrons, right here for sulfur, right? Of the 16, we said 6 of them are valence electrons. So we got 6 valence electrons. So as I'm writing this over and over again, hopefully you're understanding the trend, right? Of those 6, 10 are core electrons. So nuclear charge. How do we get the nuclear charge? The nucleus is plus 16, but we still have 10 core electrons. So you have minus 10 electrons because of the core. And so the valence electrons experience a plus 6 charge. So valence electrons experience plus 6 effective nuclear charge. I'm getting tired of writing. You can see my handwriting is changing. Okay, bottom line, because the electrons, even though there are 6 of them, have experienced a stronger nuclear charge in sulfur, guess what? The sulfur atom will be so much smaller than the magnesium. But not only that, the electrons are experiencing a very, very strong suctioning power from the core of sulfur than from the core of magnesium. What was the question again? Which atom's valence electron experience the greatest effective nuclear charge? Oh, we can see sulfur, of course. Oops. The effective nuclear charge here we saw was what? Plus 2. For this one here, 3. For this one here, it was plus 6. So this would be the strongest, which means it will have the smallest size. They didn't ask you all that, but while we're here, why not? Okay. So to answer a question that appears so simple like this one, you kind of have to analyze it at this level. It took me a while. I may make it seem seamless right now. It took a lot of practice for me to get to this point of saying, okay, now I understand. It's not just that simple. You got to go through the why, though, right? The energy levels, which ones can and cannot block. The core ones block the valence ones, okay? It did help that when I was a student in school, I was struggling. So it's a habit of mine. I would naturally pick core, not core. So I would naturally pick valence seeds. Even right now, when my husband and I are trying to do something, I go for the cheapest first. He's like, "Why do you want that?" I'm like, "Because it's cheap." And he's like, "Can we go to the core section?" I'm like, "Okay, I guess, whatever." Yeah, you gotta compromise. Okay, so we see all that stuff summarizing here. Atoms in the same group increase in size when you go down the group. Why? Because the valence electron is in a larger energy level, right? So they go through all here and they talk about effective nuclear charge. And so I'm not going to go into all this again. We have talked about the most important thing. Now we get to apply this here. So I want to talk about this question and the structure of this question. The way this question is written, you have two levels. They say here, on the basis of periodic trends, choose the larger atom in each pair, if possible. Explain your choices. So you want to choose the larger atom. That's the first part of the question. Simple, pick which is larger. The second one says explain your choices. So this is where, if it applies, you go into the whole effective nuclear charge, if it applies, right? So for this, what I'm going to do, I'm going to bring in a new page and then summarize this. So we're trying to pick the larger one, right? I'll copy this, add a new page, and then remember you can zoom in for this part. I use the old image that's not very accessible because it's kind of small, but the new one was all messed up. Okay, we're going to use periodic trends to choose a larger atom. So I'm going to work this the short way. We're doing the first part of the question first, and then when necessary, we'll explain our choices. For my first part here, they say N or F. So I pull up my periodic table, and then I write these relative to each other. They're the same energy level in the periodic table, energy level 2, right? N is left of F. Okay, then I write my trend. Size decreases from left to right. So on left, I usually have my larger size. So I write the term here, larger. On the right, I have my smaller size, right? My smaller size. Okay. And then size increases from top to bottom, right? So if I'm going this way, this is smaller size and this is larger size. Okay. Okay. So between N and F, since they're on the same energy level, all I'm going to be using is the left and right rule, right? Because top and bottom says they're the same size, but left and right rule. So since F is on the right, F is smaller, but they want the larger. F is smaller, N is larger. So I'm going to say this is larger. Okay. Based on this rule. Okay. Now for my next one, I'm going to erase these. I don't need this here anymore. I'm going to look at C or GE. So I have to look at my periodic table. How are C and GE related? C is on top of GE, but they're in the same group. So since they're on top of each other, or yeah, one of the other, then the left to right won't work because their relationship here is top and bottom. So they want the larger one. That means C is smaller. You can see that, right? And then GE is larger. Okay, so I picked GE. GE is the larger one because it's further down. That's what the rule says. So you see what I do here? When I draw that, it makes my life a lot easier. Okay, now I'm comparing N and AL. Okay, I pull up my periodic table. Where is N? N is over here somewhere. I'm just drawing a general area. But then the relationship between N and AL. AL is diagonally to the left of N. Okay, so when I look at the left and right, AL is further left. When I look at top and bottom, AL is further down. So I have to apply both rules because both rules apply in a diagonal relationship. Okay, so here they say the one that's further left is larger. These two, this is further left, right? It's further left. Therefore, it is larger. If you look at up and down, this is also further down. therefore larger. So when I use both rules, I arrive at the same conclusion. AL is larger because it's further left and further down. That's what the rule says. When you're going for the left, you're larger, you're down larger. Okay, last one. I have to compare AL and GE. So once again, I pull up my periodic table here. I don't need my N anymore now. It's in the way. Let's see how this plays out. AL is somewhere here, like here, and then GE is like that. So now they have a diagonal relationship the opposite way. Okay, so let's look at this one here. They say which is larger between these two. When I look at my left to right, so from left to right, it shows that AL is further left, right? Correct? So AL is larger. That's their conclusion. Okay? But from top to bottom, which is further down? From top to bottom, GE is larger. Okay, we have a standoff. So who is correct? Which is correct? Which rule is more dominant? Remember, the rules are made by chemists to help people who are not doing the experiments, aka students, to arrive at the same conclusion that they got to when they did experiments, right? So usually the order is you do an experiment, you realize a trend, you come up with a rule to help other people. So these rules are not perfect. That's why they have exceptions. This rule just fell apart. So when you get to this part and you can't decide because the rule doesn't work, it gives you two different answers. The tiebreaker is perform an experiment. Okay? Perform an experiment. When you perform an experiment, it helps you to realize what is going on. Okay? We can't do this right now, so you just say here it's complicated. Experiment will tell you what the answer is. Let's see how they set it up right here. So yeah, they went through all the details and said, of course, N is bigger. Yeah, when you trace the path, N is bigger. Oh, now I forgot to mention the Y. We've gone over this over and over again, right? When we're going to left to right comparison, from left to right comparison, we said the increase in the effective nuclear charge causes the size of the atom to decrease. So remember, the effective nuclear charge is what I call the sucking power of the atom, where the core is sucking on the is pulling in the outer electron and pulling it in, right? So as that gets bigger, the size gets smaller. And then of course, from top to bottom in the same group, the increase in the energy level of the outer electron causes the increase in size of atom. So hopefully, as you can see this will be the rule all the time. This would be the explanation all the time. You can see what we saw, right? And so feel free to go through here. And they do tell you that the rule falls apart here, so they have to use an experiment. It's a lot of words, but they go through that. I want to go ahead and move on because my goal is to get through this. Now, this is the part I was mentioning earlier that I didn't realize we hadn't gotten to yet, because the order of the slides usually comes differently than the way I think about them sometimes. We need to define something called magnetic properties and in metals, right? So here's where I bring in the story of, I wanted to say Wolverine, but this wasn't Wolverine, it was Magneto. I don't even know why I use these references because I'm not even good at remembering movies or sports, but if I can remember something about a movie or sports that applies, I'm going to be using it. Okay. So here we have magnetic properties in ions. We're told electronic configurations that result in unpaired electrons means that the atom or ion will have a net magnetic field. This is called paramagnetism. Okay. So we naturally assume that metals are magnetic. But in this section here, we're going to be told not all metals are magnetic. Okay. If you have an electronic configuration of an element, it doesn't even have to be a metal. That's where this one kind of gets complicated, right? It doesn't even have to be a metal. We'll see that down the road. Oh, I'm telling too much too soon. Okay. I need to keep some things to myself. But we're told in general, if the electronic configuration of any element results or compound results in unpaired electron, that means that the atom or ion will have a net magnetic field, and that is called paramagnetism. Okay. To illustrate this, they show you silver. And we're working through the configuration of silver. So I'm going to work this once again on the next page so y'all can see how this plays out. So silver is Ag, and silver has how many electrons? Many. Is that 47? It's hard for me to see it from here. 47. Okay. So I'm going to, since they have the shorthand configuration, I'm going to use that here. Why reinvent the wheel is written over here, right? So from krypton, we go to get to silver, we go to 5s2, and then 4d9. But remember, this one has that special configuration, which is going to be 5s1, 4d10. Okay. So you can see here that the one electron in the s sublevel is unpaired, right? So if you want to see it even further, you want to draw the orbital diagram. So this right here is the configuration. You want to draw the orbital diagram. In the orbital diagram, the shorthand is KR like this. And then we have the 5s first, 5s1, and then 4d10. So I'm going to draw this as a box, one box for the orbital. And remember the D sublevel has 5 orbitals. So I'm going to draw all 5 of them. Remember they're degenerate, right? 1, 2, 3, 4, 5. Okay. So this one here has 10 electrons. It's full. That's what helps silver become very stable. Up, 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 up. Down, 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 down. Okay? 10 electrons. This one only has 1, so it's up. So this is obviously unpaired. Because silver has an unpaired electron, or when I was learning this, my teacher said partially filled. I like the term partially filled better because of the way I remember things. Okay, let me share this with you. This is what, 47? Silver has a partially filled 5s orbital. Silver is therefore paramagnetic. Okay? Because it has partially filled orbitals. So the situation here is the magnetic behavior of the metal or the element or the ion arises, starts to show up because you have partially filled orbital. Why do I prefer this term partially filled versus unpaired? Because when I was a student and I was trying to remember, I said, ooh, partially paramagnetic. I know you can laugh at me. I am secure in this area of my life, this one area. You can laugh at me. I was like, remember, partially filled orbitals have paramagnetic behavior. Par. See? Hey, it helped me get it right in the exam. You can laugh at me all you want. So that's partially filled. So I like the term partially filled more than the unpaired. Okay. Electronic configurations that result in all paired electrons mean that the atom or ion will have no magnetic field. This is called diamagnetism. This metal will be slightly repaired by a magnetic field. Okay. Our example here is zinc. So zinc having 30 electrons, the shorthand they show us here, it's going to be argon, right? Yeah. Our shorthand configuration is AR Let me just look at what they're doing here. AR 4s2 3d10. 4s2 3d10. This is the configuration. You can see, I just call it conf for configuration. This is full. This is full. There's no room for any more, right? So when you draw your sub-level down here, in preparation for drawing your orbital, we have 4s2 3d10. This is up, down. This right here. D again has got 5 orbital, right? Degenerate. 1, 2, 3. There. Up, 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 up. Down, 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 down. It's full. So fully filled orbitals cause, in this case, zinc to be not para. What am I thinking? Diamagnetic. Diamagnetic. Okay, it's fully filled, not partially filled. Okay, so here they have us work on writing electronic configuration and orbital diagram for each ion and determine whether each ion is diamagnetic or paramagnetic. Okay, let's go ahead and do this. I'm going to copy this over here. I'm copying this question over here. Okay, so we're going to be doing electronic configurations for the ions, and then we're going to be working through and see what happens, okay? Wait, why is the page not added? Oh, gotta click the right thing to add the page in the right place, right? I don't know why I just click and I get the page in the wrong place. Okay, right here, paste image, get this bigger so I can actually read it. Read it. Okay. So aluminum normally has 13 electrons. I'm looking at my periodic table right here. But aluminum, so I'll write the configuration for that. Why not? For aluminum, it's 1s2, because it doesn't have that many electrons. Did I do it the shorthand way? Oh, man, they do shorthand. Let me do shorthand. For all three, right? You can do the whole thing with shorthand. No, we're trying to get this stuff done. So aluminum shorthand will be in parentheses or brackets, neon takes care of 10 electrons. After neon, we have 3s2 3p1. Okay, so aluminum, after it loses 3 electrons, becomes 3 plus. Oh, I should write the 3 plus right here. It's left with 10 electrons, right? After it loses 3 electrons. Now it pretty much has the configuration of just neon with 10 electrons, because these 3 are the electrons. Remember, let me highlight this. These are your valence electrons. How do I know that? They are the ones on the highest energy level. There's 2 here, there's 1 here, but it's a total of 3. All 3 get lost. So now aluminum has 10 electrons left, and it has the configuration of neon. So now that we have the electronic configuration of aluminum with 3 plus, they want us to draw the orbital diagram. So we're drawing the orbital diagram of what remains. So in this case here, we're kind of drawing the orbital diagram of neon. That's what they do here. So I'll just draw the orbital diagram of whatever remains, right? So the remaining configuration that has 10 electrons, mine will be slightly different from theirs. Because I'm going to draw it for all 10. They draw it for the last. So when aluminum ion only has 10 electrons, the configuration is 1s2, 2s2, 2p6. This is all we have left. 1s2, 2s2, 2p6. This is the configuration. So technically, I've finally written the first part. Okay, the full configuration. I didn't do the shorthand. Okay, now they want the orbital diagram. For the orbital diagram, what I'm going to do here is I'll draw them for everyone, for every sublevel. This is a 1s sublevel here. This is a 2s sublevel. This is a 2p sublevel. I don't want to complicate it yet by putting these at different levels. You know, if you want, you can do that. 2p sublevel. Remember, 2p sublevel has 3 orbitals. These all tie in together, right? 1s, I'm going to put 2 electrons here, up and down. 2s, 2 electrons, up and down. 2p, 6 electrons, up, 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 down, down, down. 6 electrons, right? So here I have my configuration config. Then here I have my orbital diagram, orbital DIA. G sounds more like a shorthand. And then what were they asking? They asked for configuration done, orbital diagram done, then determine if it's dia or para. Ooh, okay. Check, check, check. All the orbitals are full. Fully filled orbitals produce diamagnetic situation here with aluminum. Okay, so aluminum 3 plus with only 10 electrons is diamagnetic. As I said, I drew all the electrons, so this part is done. Diamagnetic, we got that. Next one we're going to be looking at is sulfur. Now sulfur has a lot more electrons, so with this one here, even after I add the electrons, I'm going to be drawing the outer energy level. Okay, so we're looking at sulfur next. Sulfur normally starts off with 16 electron. The configuration with 16 electron is, we're doing the shorthand, right? Shorthand is neon, right? And after neon, we go to what? Energy level 3. 3s2 and then 3p4, right? Neon handles 10 electrons. The remaining 6 are here. 3s2, 3p4. We got that. Now they said sulfur has to gain 2 electrons. Let me check to make sure. Sulfur is gaining 2 electrons. So we go down here and we see sulfur now has 2 additional electrons. That means the total electrons we're working with now is 18. So we're dealing with still neon that takes care of 10 of the 18 electrons. We still have 8 more to place. We put 3s2 here. Now we add the remaining 2 electrons here. We have 3p6. So this will be our config for our configuration. And then I have to do what? Oh, orbital diagram. Remember, I like to draw my orbital diagram from the configuration. So I'm going to draw here neon. I'm going to do the shorthand version of this one here. 3s2. I'm going to put my 3p6 here so I have enough room. Okay. 3s2, s's get 1 orbital. P's get 3 orbitals. 1, 2, 3. These are the degenerate, the 3 degenerate. I remember watching a country movie where they're like, they're degenerates. I'm like, you mean same energy level? They're talking about them being criminals and like acting bad and stuff like that. I'm like, this is the terminology, y'all. Right. These are not criminal orbitals. They just degenerate the same energy level. I'm sorry, y'all. This is how my mind works. It just connects things all over the place. Where was I? Up, down. Right. We got 6 electrons in these orbitals. Up, 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 and then pair them down, down, down. There. Okay. Oh, we're checking to see if we have a partially filled. Nope. Neon. Sorry, our element was sulfur, right? So sulfur, after it's gained 2 electrons, to now have 18 electrons, has fully filled orbitals. How do I write it here? And therefore, it is diamagnetic. Oh, I managed to get a C in there. Okay. Now let's look at this last scenario. In this last scenario or in this last situation here, we're looking at iron 3. Ooh, iron 3 is that D block element. D block elements are full of surprises, right? They're not predictable. Their behavior is not predictable. So let's look at iron so we can look at iron 3. Let's look at iron by itself. Fe. Fe starts off with how many electrons? 26. Okay, shorthand configuration for Fe is Ar in parentheses. Ar handles 18 of those electrons. From Ar, we go to 4s2, and then 1, 2, 3, 4, 5, 6, 3d6. Okay, So they want our iron to lose 3 electrons. Okay, we can do that. So remember, what are these called again? Transition elements, sorry. Transition elements lose electrons from s orbitals before d, or so I should say from s orbitals before d orbitals. Okay, this is the rule I am remembering, and this is the rule I am applying here in what I'm about to do. Okay, so they wanted us, when I say they, the author, right, to have iron lose 3 electrons. So when iron loses 3 electrons, they will be left with 23 electrons. Okay, so in our configuration, argon is still at 18. We're still going to use that. We can still use the shorthand because we have more than 18 electrons, right? Argon will be at 18. And then 18, y'all bear with me as I do this in my calculator. I know I can do it in my head. I know 23 minus 18. It felt nice to do something different. 5. So when we place 18 here with argon, I have 5 more electrons to place. Remember this rule. I have to take my 3 electrons out from uh, 4s first, right? Before D. So now I take 2 of my electrons from 4s, because it's only 2 to take, right? And then the third one I take from 3D. So now 3D only has 5 left. 18 plus 5, 23. This is my configuration for the iron. Say that quickly. Okay, so we're here. Now we have our configuration. Config done. Config done. Now we're going to move to our orbital diagram. So for orbital diagram, once again, for 23, I'm beginning to see things that are not there. Fe, 3 plus. This is AR. This is 18. I want to space out my 4s0 is empty. I would still like representation, right? Because it used to be part of us, now it's not anymore. So I'm going to draw this orbital diagram empty. And then my 3D now has 5 degenerate orbitals, right? 1, 2, 3, 4, 5. Got it. Okay. Remember, was it Hund's rule where you have to go in and fill in one orbital before you pair? Up, 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 up. There. This is our orbital diagram. So I'll call it right here. Orbital DIAG diagram. Okay. Iron has 5, not just 1. Partially filled. Remember that? That's my preferred word. Partially filled 3D. Partially filled 3D orbitals. It is therefore paramagnetic. Done. Okay, so of course they go through here and explain stuff in a more beautiful type way. They even have pictures. We're done with all of this. Okay, you can feel free to read the dialogue they write, because even though I am paraphrasing and stuff, you want to make sure you understand this. So now we're talking about the radius of the atom and their ions. Okay, so I'm going to keep going through this as we explain this part here, because yeah, this will help you guys finish the one lab. I'm gonna let's see. I think I can make it to the end. Yeah, I'll see how it goes. I have a target time where I'll stop talking. Okay, so right here, the bottom line when it comes to ions and their original atom is you want to look at what is happening. Are we gaining or losing electrons? Okay, so with this part here, I won't go into all the deep explanation. I already did that before in the previous video I shot today, because I pressed stop at some point. The cation radius is smaller than its corresponding atom radius. The loss of electron results in the remaining electrons in the atom experiencing a larger effective nuclear charge than the neutral atom. Okay? So I'm going to go back to that whole effective nuclear charge just one more time, and then that will be it, y'all. One more time. So what's happening here is because, if you were in the 4-year college, they will go through all of this, right? They will. Plus, for those of you who are going off to organic chemistry, I don't want to skip on this part so that when you get there, all of this is brand new and then you're totally overwhelmed. At least you've heard it one time here. Okay, so how does the effective nuclear charge influence the size of the remaining? In this case, we're told that let's look at something that's losing electrons. Lithium. Lithium loses one electron, right? So the lithium element, let me draw lithium element here. Lithium on my picture here, on my periodic table, is an energy level 2. So the lithium nucleus is here. It has a plus 3 charge because of the plus 3 here, atomic number. I need 2 energy levels, 1 and 2. So the picture I have on the left of the atom is lithium atom, right? I have my 2 electrons here in the middle because energy level 1 can only handle 2 electrons. Energy level 2 total can handle 2 can handle up to 8 electrons. But we have the first 2 here, the third one right here. On the right, I'm going to show what lithium looks like after it has lost its 1 electron. Lithium has now lost 1 electron. It only has 2 electrons left. Okay. The nucleus is still plus 3 because the only thing that got lost is the electron, not the proton. So the nucleus has not changed. It is still plus 3. The energy level 1 is still here with 2 electrons. Now I'm going to show you energy level 2 to show you what happens. Energy level 2 here has a 1 electron, right? So in the process of making the ion, in the process of getting rid of the electron, not only does the electron go away, so does the energy level. So in essence, you remove the electron and the energy level like that. Bam. So you can see instantly the size of the ion is smaller, right? Because you only have one energy level where the electrons are located. And not only that, these electrons here, these electrons used to be core electrons. Remember back here, they used to be core electrons living that core life. And this 1 electron here was the valence electron. Once that 1 electron got removed, guess what? They got downgraded. Not really downgraded. They are now the new valence electrons. So remember, the size of the atom, the ion, whatever, boils down to the nucleus pulling on the valence electron. So now the nucleus is pulling on this valence electron and is pulling it with a greater charge, with a greater effective nuclear charge. As I go deep, over here, effective, so the 2 reasons why the size is smaller. Effective nuclear charge, I can write better. Hold on, let me write for left. Effective nuclear charge becomes plus 3. Because notice these 2 electrons that are now the new valence electron don't have any other electron in front of them blocking them. Back here, though, the effective, which I didn't calculate earlier, nuclear charge is going to be what? Effective nuclear charge is going to be plus 1. So the effective nuclear charge increases because here the outermost electron is being blocked by the inner electrons, right? So remember, the overall charge of the nucleus is plus 3. The inner electrons neutralize that a little bit, and then the outer electron experiences plus 1. Yeah, so 2 reasons causes the size of the ion to be smaller. One, effective nuclear charge increases. Second one, you can say loss of valence electron. So going back here, they talk about all this stuff. The loss of electron results in the remaining electrons in the atom experiencing a larger effective nuclear charge. Right. All the electrons left over now experience a larger effective nuclear charge. And so for that reason, all ions, because you're losing that layer and the remaining electrons experience a greater attraction, are smaller. So when you look at this here, the pictures on the right, or the half circles on the right, are showing you the relative size of the ion compared to the original element, atom, right? So you have atom, ion. Bottom line, because ions are losing electrons energy level and then the suction power increases, the size of the ion is smaller. So I'm going to summarize this in a picture, or it's not really a picture, and say cations, which represent positive ions, are smaller than the atom. Remember, the atom is neutral. Cation is smaller. Atom is neutral. So this is relatively larger. Okay. The second part here is radius of the atom and their ions. So over here it says when atoms form anions, electrons are added to the valence shell. The new electrons experience a smaller effective nuclear charge than the old electrons. Why? They experience a repulsion from the existing electrons. So to kind of explain this here, I'm not going to go into all the details. Feel free to look at all that stuff here. Oh, I did it in the right place this time. Yeah, I think I'll stop in 15 minutes. I'm beginning to get a little. Oh, I guess it's time for my snack. I'm beginning to get a little hungry. Yeah. Okay, where was I? Yeah, in this picture here, all the atoms are on the right. I mean, sorry, that's not the right. That's the left. My bad. That's like the true left atom, and this is the anion, right? The negative ion, anion. So you can see here in general, the anion is larger than the atom. So you have the atom smaller than the anion. Okay. So the way I try to visualize this is as you add the electrons come in, and then what they're saying here is that the additional electrons, the newer electrons, because they're more pre-existing electrons, have even less pull from the nucleus. For that reason, the new valence electrons will experience less attraction to the nucleus, and for that reason, the size will be larger. I won't over explain that because that's not usually a very common thing that you have to go over again. Just remember, the anion tends to be larger than the atom. This is smaller between these two, right? In the previous slide, I said the atom is relatively, oh, hold on. The atom is relatively larger compared to the cation. So if you have this general trend down, I think it's a good trend to have. If you're asked to compare the three together, and the other way of looking at this is this: the overall size of the atom is influenced by the number of electrons. The more electrons you have, the larger the size. If that logic works for you, then go with this. Remember, size of atoms in general, this is very general, increase as number of electrons increase. And this is a very, very general statement. Increase, right? Increase. How do I spell increase? Increase. I'm obsessed over the spelling. Okay, so which one has extra electrons? Anions have extra electrons. So guess what? They will be larger. Between these two, this one here will be, compared to that, the atom will actually be intermediate because it doesn't have any extra. It hasn't lost anything. Then the one that relatively has less electrons, the cation, so this will be smaller because it has lost electrons, right? You lose electrons, you're losing some size. You gain electrons, you have extra size, extra girth, right? Extra bigness or fluffiness in the atoms. So the size of the atom in general. So later on, when scientists are referring to this, they casually say, well, there were more electrons, so the size were bigger. And we're like, oh, okay, we get that. More electrons, larger size. Less electrons, less size. Okay. So from here, we'll work on this problem here using that analogy. More electrons, more size. Or larger size. Yeah, that's the proper way to say it. Okay, let me look at this problem right here. We will work on this. Is that what I'm working on right now? Right here, add page. So you know what I'm gonna do? I'm actually gonna I'm trying to think of it because I'm actually gonna work on this one last, and then the remainder of this ionization energy, I will finish that when we meet next week because it's not a whole lot. And for the part with the ionization energy, I don't know why I just feel more. Yeah, I'll see. I'll see how I feel after I'm done talking about this because when I get hungry, it does affect my focus level. So kind of a little hungry right now. So I'm really thinking about food. I shouldn't be. Electrons, electrons. Okay. Here, choose the larger atom or ion in each pair. So I have that copy. Did I copy that already? Copy. Then I'll press this down here. Okay. Choose a larger atom or ion in each pair. So we have sulfur versus sulfur 2 minus. It's obvious this one here has extra electrons, therefore larger. Plus we said the anion is larger anyway, right? So you can say anions are larger than atoms, right? First one done. Second one, calcium versus calcium ion. This one here has lost 2 electrons, right? Indicated by the way this is written, the symbol. So this will have to be larger. Larger because atoms are larger than cations. Okay. The last one we have this. Ooh, these are different elements. Let's see what they have in common though. Br minus versus Kr. Okay. So Br by itself is what? Br by itself is not is, has 35 electrons. Kr by itself has 36 electrons. So when Br becomes Br minus, it gains 1 electron to become 36. Kr, nothing changed, it's at 36. So the number of electrons in the end are the same. So what makes Br larger? Br is larger. Br is larger because technically it has a new electron, right? It has a new valence electron. And it is an anion. So you can go by that rule that anions are larger than neutral atoms. Okay. So what I'm gonna stop here because as I was working on this, I was thinking about this. I do have the recording available, right, for the previous semester. So the whole point of me doing this is to talk to people. So I'm gonna stop right here, and then we'll continue this next time. Okay. So Monday, right? We'll continue on Monday. Have a nice evening. Okay. Bye.